Okay, we're first going to start out with the information that we were going over that I introduced a little bit yesterday in the laboratory, and that is significant figures and calculations. On Thursday of last week, I introduced how to read a measurement, how to determine the number of significant digits you are to record with that measurement. What comes next is performing calculations, some of which you did yesterday in lab, but we're going to go into it in further detail. So, first of all, when you're dealing with addition and subtraction, the results will carry the same number of decimal places as the quantity with the fewest decimal places. In other words, it is the number of decimals that matter in addition and subtraction. So an example, we have 2.345 plus 0.07 plus 2.9975. Again, when we're dealing with addition and subtraction, well, let's first start out. Those three numbers add up to be 5.4125. When you're dealing with addition and subtraction, the answer will have the same number of decimal places as the measurement with the fewest. Since the fewest number of decimal places was 2, we're only allowed 2 digits in our answer. Therefore, this would be recorded as 5.41 as an answer. In the next problem, we have 5.9 minus 0.221. Because the measurement with the fewest decimal places had only 1 decimal place, our answer is only going to have 1 decimal place. Now, we always look to the number immediately, the first number we're going to drop. If the first number you're going to drop is 4 or less, you do nothing. If the first number you are going to drop is 5 or more, you round up. So therefore, we would round this to 5.7 as an answer. Questions? So that is addition and subtraction. Again, when you're dealing with addition and subtraction, it is the decimal places that matter. For multiplication and division, the result will carry the same number of significant digits. As the quantity with the fewest significant digits. In other words, when you're doing multiplication and division, the total sig figs is what matters. So let's look at an example. I have 1.052 times 12.054 times 0.53. This is multiplication and division. So significant digits matter. The first number has 4 significant digits. The next number has 5 significant digits, and the last number has 2 significant digits. Because the number with the fewest is 2, our answer can only have 2 significant digits. Looking at the number immediately, the first number we're going to be dropping, since it's less than 4, we don't round, and therefore we would record this as 6.7. In our next example, I have 2.0035 divided by 3.20. This is multiplication and division, so total sig figs matter. In the first example, I have 5 sig figs. In the last number, there are 3. Since the number with the fewest is 3, our answer can only have 3 sig figs. Looking to the first number we drop, since that is 4 or less, we do nothing. And therefore, we would record this answer as 0.626. Don't worry, we're going to figure out how to determine the number of significant digits here in just a few minutes. Questions? So again, if it's addition and subtraction, pay attention to the decimals. If it's multiplication and division, pay attention to sig figs. And you will notice with rounding, I always looked to the first digit I was getting rid of. And if that first digit that I was getting rid of was 4 or less, I let it be. If it was 5 or more, I rounded up. The same thing will happen to your grade at the end of the semester. If you're within 0.5 or more, I will round up. If it's with 0.4 or less, I will not round. Where it gets complicated is when we have multi-step calculations that contain multiple orders of operation. When we have multi-step calculations that contain both addition and subtraction and multiplication and division, the rules are different. So how do we treat them? Well, number 1, you don't round until you're at your final answer. But you have to pay attention to each operation. And what we do is we always keep 1 extra digit, and we make note of the fact that we're keeping that 1 extra digit. And then also we use PEMDAS. So we do parentheses and exponents first. Then we do any multiplication and division second. And then we do addition and subtraction. Now, if it contains parentheses and exponents, you do them left to right. If it contains multiplication and division, you do it left to right. And addition, subtraction, you do it left to right. But you do it in this particular order. It's just if it has multiple additions and subtractions, we do it left to right. I'm going to show examples, or an example. Which again, folks, if you're doing the flipped classroom videos, you're getting most of this information, and I can speed through the information and get to the examples. That's one of my goals, is to do mostly examples. So here is a multi-step calculation. We have 5.78 times 5.903 times, open parentheses, 5.489 minus 5.01. We do the parentheses first, because that's the first thing in PEMDAS. When you do the parentheses, you get a number of 0.479. According to addition and subtraction rules, it is the decimal places that matter. Therefore, you have 3 decimal places and you have 2 decimal places, so your answer should have 2 decimal places. That is why you have, but because this is multiple operations, we're going to carry that extra 1, but we're going to make note of it by underlining it. Saying this number, that 9, is not significant, but I can't drop it until the end. You can't do any rounding until the end. So you make note, I gotta keep it, but it's not significant. So I'm underlining it so that I remember it's not significant according to the rule. Now I have multiplication and division. And when I look at this multiplication and division, my first number has 3 significant figures, my second number 4 significant figures, and my last number only has 2, because again, that 9 is not significant with respect to the number of decimal places I should have had according to the addition subtraction rule. So therefore, my answer can only have 2 significant digits. Well, that would be the 19. And then I look to the digit I'm going to drop, and since it's less than 4, I'm going to drop it, and therefore the answer would be 19. Yes.
So, I see where you would underline the 9, but if it's only 2 decimal places, why would you not underline anything on the 5.9?
The 5.903 is part of the original problem. It is only, basically what we've done is we've taken this parentheses and we've gotten the answer for the parentheses.
Okay.
Because we have to do parentheses first. Then we could do all the rest of it with multiplication and division.
Yes.
Other questions? Please ask. I want to clarify.
So the 2 significant digits above the 0.479, that comes from how many significant digits are in 5.01?
That comes from, no, that comes, so you can almost think of this as a funnel effect. To get this 0.479, I did addition and subtraction. Decimal places matter. There were 3 decimal places, there were 2 decimal places. So that's why this only has 2 decimals. But you can't get rid of the number until the very, very end. Because that 9 may make a difference in this answer. You don't know. other questions? Let's look at some examples. Now I got to get my calculator out. Okay. So what I see is all multiplication and division. So it is sig figs that matter. I have 3 significant digits in my first number. I have 4 in my second number. I have 5 in my third number, and I have 5 in my fourth number. When I key this into the calculator, I get an answer of 0.65219, and it continues. But according to the number of significant digits, 3 is the minimum. Therefore, my answer can only have 3 significant digits. So it's the 6, 5, and 2. Looking at the digit I drop, it is less than 4. Therefore, the answer for this would be 0.652. Questions? Yes.
So all zeros after the decimal place count as a significant digit.
Zeros at the end of a number after the decimal count as significant, but zeros before the first non-zero are not. We'll get to that. We're going to get to that more here in a few. Let's look at another example. This I see is all addition and subtraction. What in the world just happened? Therefore, it's the decimal places that matter. I have 3 decimal places. I have 1 decimal place. I have 4 decimal places. The fewest decimal places is 1. So when I do get my answer, it is going to be 1 decimal place. When you key this into the calculator, you get 4.873. Again, I carry to the first decimal place. I'm looking at the number immediately following it. It is 5 or more. Therefore, I'm going to round up. So this answer would be 4.9. Let's look at another example. Okay, this one I see has multiplication, divisions, parentheses, and addition, subtraction. The first thing I'm going to do is I'm going to take care of what's in the parentheses. This is addition and subtraction, so the decimal places matter. So I had 4 decimal places and I have 2 decimal places. The result of that calculation comes out to be 0.3455 5, but I'm only allowed 2 decimal places, so I'm underlining the numbers I would have dropped. Now I can take and do the rest of this math. Because now it is all addition, multiplication and division. So significant digits matter. In the first one, I have 4 significant digits. In the next one, I have 6 significant digits. And in my last number, I only have 2. Keying that into the calculator, you get 52.799, but I am only allowed 2 significant digits. So I'm allowed the 52. So I look at the digit that comes after that, that is 5 or more. Therefore, I'm going to round up. So this answer would be 53. Yes.
You kept both of the 5s and 0.3455 for the calculation, but didn't it say you just keep the first number that you got?
You can keep one, you can keep all of them. It does not matter. You just have to keep one of them. You have to keep one of them, but you can keep all of them. It does not matter. What does matter is paying attention and noting, okay, these are the only 2 that are significant. The rest of it was insignificant. Questions? Okay, so up until this point, when we've been dealing with multiplication and division, I've been telling you how many significant digits there are. Now, let's look at how to figure out those significant digits. How many significant digits are in a number? First rule is all non-zero digits are significant. So anything from 1 to 9 is going to be significant. Ignore the 0 here. I just liked the graphic. All non-zero digits are significant. So anything from 1 to 9 is going to be significant. Where it gets hairy is what happens to the zeros. So let's look at the rules of zeros. Interior zeros are significant. One of the things I'm going to tell you over and over is when I do these problems, I identify the first significant digit, I identify the last significant digit, and then everything between those goalposts are significant. So I use my rules to identify the first significant digit and the last significant digit, and then anything in between those goalposts are going to be significant. It doesn't matter whether it's a non-zero digit or a 0 digit. If it's between, it's significant. So interior zeros are significant. The next one, leading zeros are not significant. The way I like to view this particular statement, don't even start counting until you get to your first non-zero digit. Don't even start counting until you get to your first non-zero digit. Because leading zeros are not significant. Now, those 2 rules are straightforward. The rule what is challenging are your trailing zeros. Or zeros at the very end of the number. Talking the last zero in the number. Is it significant? Is it not? Well, if the last zero in the number is after a decimal point, then it is significant. If the last zero at the end of the number is after the decimal, then it is significant. But if the last zero is before an implied decimal point, like 100, 20, 77,500, any of those zeros at the end of the whole number where it is before an implied decimal point, those are not significant. So 100 has only one significant digit. $20 has only one significant digit. 75,000 has two significant digits. Questions? We're going to do some examples here in a minute. So, using those rules, number one, I don't start counting till I get to my first non-zero. Then I look at everything to follow. This zero, first of all of these non-zero digits are significant. The in-between zeros are significant. And trailing zeros are significant if they are after the decimal point. So this number has 5 significant digits. Questions? Or in other words, we have non-zero digits, rule 1, rule 2, rule 3 for your various zeros. So if we're looking at the number 21,000. These two are significant. But the zeros are insignificant because there's an implied decimal point. And zeros prior to an implied decimal point are not significant. Now, let's talk about scientific notation because we're going to deal with a lot of scientific notation. We deal with a lot, I mean, after all, if you think about an atom of an element, its diameter is roughly 1 times 10 to the minus 10. If you think about a mole of something, it's 6.022 times 10 to the 23rd. If you think about Planck's constant, it's 6.626 times 10 to the minus 34. If you think about a wavelength of light in the visible region, it's times 10 to the minus 7 meters. We deal with a lot of scientific notation. So how do we determine the number of significant digits in scientific notation? Well, it's quite easy. If it's in the coefficient portion of a number in scientific notation, it is significant. If it's in the coefficient portion of a number in scientific notation, then it is significant. Folks, these exponents are going to tell us how many trailing zeros at the end of a whole number there are. Or they're going to tell us how many zeros at the beginning of a number there are. That's what the exponent is there for. But this portion tells you how many significant digits there are. So let's look at some numbers. Ooh, some of it's not very visible. The very first one is 45,000. How many sig figs are there? There are 2. Because trailing zeros in a whole number are not significant. So only the 4 and the 5 are. The next number, 140.00. How many significant digits are there? Oh, I got lots of different numbers. Let's talk about this. First of all, we know the 1 is significant because it's a non-zero. As I said, I tend to look at the first number and the last number and then figure it out. So I look at this number. Are zeros, are trailing zeros that come after a decimal point significant? Yes. So once I've said that 1 and that 0 are significant, then I got goalposts. Meaning everything in between is significant. So this had 5 significant digits. How about 28.03? There are 4. How about 0.00540? I heard a couple of different numbers. There are, first of all, don't even start counting until you get to your first non-zero. Then look to the end. This is a trailing 0 after the decimal. Is it significant? Yes. I've just built my goalposts. Everything in between is significant. Therefore, there are 3 significant digits. The next one's hard to read. It's 408. How many significant digits are there? I heard 3. The next number is 7.0301. Raise your hand. How many are there? There are 5. The 7 is significant because it's a non-zero. The 1 is significant because it's a non-zero. I just built goalposts, so everything in between is significant. So there are 5. $2,500.55 has how many?
6.
There are 6. What? You changed it up again. 1.2 times 10 to the third. This is that scientific notation I was talking about. It's supposed to all be in one line. How many 6/8 are there? 2, because there's only 2 numbers in the coefficient. What about 1.200 times 10 to the third? 4, because there are 4 numbers in the coefficient. And finally, 3.5600. I hear 3 and I hear 5. So let's answer that. We know the 3 is significant because it's a whole, it's a non-zero. This 0 at the end of the number, it is after the decimal point. So that's a trailing 0 at the end of the number after the decimal. So it is significant. So there is a total of 5. Questions? Okay. Now, this is sometimes the most trickiest piece, is knowing when you have an exact number, because an exact number has an infinite number of significant digits. Exact numbers, when we have an exact number, we don't worry about them when it comes to our calculations, because they're not going to be the controlling factor. So what are some examples of exact numbers? I have 72 students in this class. That is going to be an exact number, because I can't have a half of one of you. In other words, counting numbers are exact numbers. 12 eggs in 1 dozen eggs. Those are both counting numbers. So they're going to have an infinite number of significant digits. 60 seconds in 1 minute is a counting number. It's going to have an infinite number of significant digits. Your SI prefix system, which we will go over, both sides of that equality are going to be exact quantities. 1,000 milliliters in 1 liter. That's an exact quantity. Therefore, it's an unlimited number of significant digits. Integral numbers, numerical digits, in other words, numerical numbers that are part of an equation. They're going to be exact numbers with an infinite number of significant digits. For example, the diameter is, or excuse me, the radius is the diameter divided by 2. That 2 is an exact quantity with an unlimited number of significant digits. 4/3 pi r cubed. The 4/3 is going to be exact quantity. 4 divided by the 3. They're going to have an unlimited number of significant digits. Some additional ones. When we start doing the molar mass of a compound, It's going to be the number of grams of a substance per 1 mole. That 1 mole is going to be an exact quantity. When we deal with the Avogadro's number, 1 mole of anything is equal to 6.022 times 10 to the 23rd of a thing. That 1 mole is going to be considered an exact quantity. When we deal with molarity later on, we always say something is, let's say something is 2 molar. That means it's 2 mole per 1 liter. The 1 liter is going to be an exact quantity. And in density, the implied 1 milliliter or the 1 centimeter cubed is going to be an exact quantity with the density. What we're going to find out, folks, for the most part, when we do our conversions, our conversion factors oftentimes will not impact the number of significant digits we pay attention to in our calculations. The reason that our conversion factors often do not impact the number of significant digits is because they're either exact quantities, such as the ones I just gave you, or they have so many decimal places that it, depending upon which table you look at, that it really doesn't matter compared to the numbers you're given in your problem. So most, I would say 99% of the time, the numbers that are given in the problem itself are the numbers you pay attention to with respect to calculations. Questions? Okay, so if you'll recall, one of the things I have said is that quantity without a unit is a meaningless thing. A quantity without a unit is a meaningless thing. So let's talk about units of measurement. There are a number of conversion factors that we could use when we're talking about units. There are a number of types of units out there. One of the types of units that you will encounter is the System International unit. Length tends to be measured in meters. Mass tends to be in kilograms. Temperature is in Kelvin. Time is in seconds. The amount of substance is in moles. And we don't tend to use amp or candela very often. These are examples of these are the System International units. We do sometimes use length, mass, temperature. We do use temperature, we use time, and we use the amount. But in chemistry, we run into a problem with some of these system internet being able to use just strictly SI units. The problem is a meter is quite large. And most of our substances can't be measured with meter stick. A kilogram? I mean, yesterday, what did you use? Grams. We don't tend to use kilograms. About the only time you start using kilograms is when you get into industry. When you're producing mass quantities of a material, then we might get into kilograms. But we don't tend to use kilograms otherwise because it's just too big. So we tend to use the metric system. When we talk in the terms of the metric system, length is still a meter. But when we mass is in terms of grams. Volume is in terms of liters. We will use time. We will use energy in the terms of joules. And temperature, again, comes out in Kelvin. So we tend to use more of the metric prefix system as our units in the laboratory than we do the System International units. Simply because the substances we are measuring are just too small. Okay. So let's talk temperature. There are 3 temperature scales. There is the Fahrenheit scale, which in the US, that is what is reported on the television for our weather. I say in the US because, to my knowledge, every other country reports it in Celsius. And then there's the Kelvin scale. In the chemistry laboratory, and for the most part, in this class, you're mainly going to have to go between the Celsius scale and the Kelvin scale. But every once in a while, Fahrenheit will creep in. It's kind of important when when you're doing mathematical calculations, you need to be able to think about what's going on. Think, does this even make sense? So it helps to have some sense of what the equivalencies are. 0 Celsius, 0 degrees Celsius is 32 degrees Fahrenheit, meaning the Fahrenheit scale is larger in its increments than is the Celsius scale. 0 Celsius, which is the freezing point of water, is equal to 273.15 Kelvin. Now, the neat thing about the Celsius scale and the Kelvin scale is their increments are the same, they just start out at a different point. And we know their increments are the same because 100 degrees Celsius is where you have the boiling point of water, and that's equivalent to 373.15 Kelvin, meaning that there's 100 increments between 0 and 100 degrees Celsius, and there is 100 increments between 273 and 373.15 Kelvin. The difference is the Fahrenheit scale starts out at a different point. The reason it starts out at a different point is because what is 0 Kelvin? 0 Kelvin is where all molecules, all vibrations, all everything stops moving. Even the smallest of molecules stops moving at 0 Kelvin. Hence, it is known as the absolute temperature scale. So, conversions. Oh, why did it do that? Okay. That is supposed to be an open parentheses and a closed parentheses. I am not entirely certain why it did what it did. On a test, you will receive degrees Fahrenheit equals 1.8, open parentheses, degrees Celsius, close parentheses, plus 32. There are other variations to that particular equation, but I do give you that equation on an exam. This equation, like I said, the 2 and the 3 are supposed to represent parentheses. I don't know where the 2 and 3 came from. I'll have to watch it more carefully as I go from my computer to my iPad. You can memorize the other variations of this equation and use them, but that's the one I'll give you in order to convert between degrees Fahrenheit and degrees Celsius. For the Kelvin, that's easy. Kelvin is degrees Celsius plus 273.15. And again, you will receive this equation on an exam. You just have to be able to manipulate the algebra. So let's look at an example. A sick child has a temperature of 40 degrees Celsius. What is the child's temperature in Kelvin and in Fahrenheit? Okay, so the very first one, we're asked to go from degrees Celsius to Kelvin. The equation is that Kelvin is equal to the degrees Celsius plus 273.15. Therefore, Kelvin is equal to 40.00 plus 273.15. Or in other words, it's 310.15. 315. That's why I was going to my calculator. My brain is not wanting to add. 313.15. This is addition and subtraction. So it's the decimal places that matter. Both of them had 2 decimal places, therefore we report our answer to 2 decimal places. Now let's look at the degrees Celsius to Fahrenheit. Degrees Fahrenheit is equal to 1.8 times the degrees Celsius plus 32. In this equation, the 1.8 is going to be considered an exact number, as will the 32. Therefore, they are not going to have any impact on the sig figs. So the degrees Fahrenheit is equal to 1.8 times 40.00 plus 32. Or in other words, the degrees Fahrenheit is equal to 104.0. If you just look at your calculator, it's 104. But it had to be 104.0 because I needed 4 significant digits. Questions? That's another another calculation, but. Okay, folks. I've already told you, you're gonna get your formulas on a test. I get formula sheets. I don't make you memorize formulas. There's only a couple of formulas you'll be asked to memorize all semester long. Most of it will be given to you. Conversion factors. I tend to give you most of your conversion factors. The only ones I don't give you are right there. This is one of the few sets of information I make you memorize. The rest is knowing how to work with things. But this, as far as conversion factors, you have to have memorized. So if you want to take a picture, so you can start memorizing it, take your phones out and take a picture. Or you can write them down. Or you can use the notes. I don't care. But you have to have these memorized. We will be working with these on Thursday and a little bit on and some on Tuesday. You have to have your metric prefix conversion factors memorized. The only other conversion factor I make you memorize is what a cc is. A cc is a cubic centimeter, which just happens to be the same thing as a milliliter. So 1 cc or 1 cubic centimeter is equal to a milliliter. I make you memorize that one because I know a lot of people that are planning to go into pharmacy or medical school. And guess what they typically use? CCs. But you need to know that it's also a milliliter. Now, next week, we're gonna talk about units and volume. Because we're getting into, and we'll get into, I mean, not next week. Ooh, Thursday. We'll talk about units and volume. We'll get into density. We'll get into energy. We'll get into conversions. And that's where I'll pick up at the start of class on Thursday. We have no lab because it's a holiday. Yep, you get a 3-day weekend.
Specific direction you would like this.
Yes, but, and are you the 8, 11, or 2? Okay, that's on top. Hey,
Statement of problems just work that you're forcing significantly for these two exact numbers.
correct,
Okay, now how were they exact?
because they are values that are part of a formula.
Okay. So the number that we add would be our significant.
That's the determining factor in that equation. Yes.
Do you have a concept?
I don't.
Could I run and go get the, yeah, I
Yes.
forgot it in my.
Yes.
I turned in the other page of it, but I do have a question.
Okay.
So when we were talking about the trailing zeros,
Uh-huh.
it was like, if it was 100, there was only one.
Correct, because it's the decimal in 100 was assumed.
Okay, so what's the difference between that and an exact number? Like how, what's the,
The way you're going to have to, basically, if I will specify what I'm counting.
okay,
So it's, you can determine it from an exact, a number, from an exact number based off of the unit.
okay, thank you, thank you.
I do have a question here. To have like for the trailing zeros, we do have to have a signal, sig before the decimal to count like the trailing zero as.
Those are not, okay. So when we say the word trailing zeros, we're talking the zeros at the end of it, the number itself. So we're talking about that zero. We're not talking about zeros after a trailing zero. The word trailing literally means at the end of the number.
Okay, thank you.
You said we don't have lab Monday, or we just push it back, or we just not have it next week.
Well, there's not one on the schedule next week
Okay.
either. So, yeah, because I already took into account there's a holiday next week.
Yes.
Yeah, I'm trying to turn my like my other roommate should have turned everything else, but I have the Excel sheet. for my
Okay,
group.
do you have the name? You're in the 8?
8 a.m. Yes.
That's that high.
That's the 11th. That's in your hand.
That's the 11.
This goes to that.
Okay, okay.
Thank you. So the first one. Awesome. Yeah, I was trying to print it off, but there was like in the library before class. And there was someone was just printing a whole book, and I didn't realize they were like just like
Oh, yeah.
printing that. And I put it on the printer. It's like I'm like, I wonder why all those pages are coming out right now. And I'm just realizing,
Gotcha.
that was.
Oh, don't forget to turn it in.
Oh yeah, sorry. My brain just that was kind of funny. Hope you have a nice day.
You too. I am not fast enough.
Dr. Yardley, are you going to your office after this?
I am. Okay, sounds good. Yes, I am headed that way.